that involve divergence and or curl. So, messy differentiation exercise. One on the exam won't be as messy, I promise. Okay. We have surface integrals. And just like with line integrals, there are two kinds. There's the surface integral of a scalar function. So that would be f of your parameterization substituted in, and then you need the magnitude of this cross product. So you compute the partial derivatives of your parameterization with respect to u and v. That gives you these two vectors. You take a cross product, you get magnitude, which would be a square root of a sum of squares again. And then that is what you integrate. So it could get kind of messy. Okay. Or, for a vector field, it's going to be the vector field of your parameterization substituted in, dot product with Ru cross Rv. So here you compute the magnitude, here you just take the vector itself and do a dot product. So there's no square root creeping in there. du dv. So expect the surface integral of each type to pop up, depending on whether you're given a scalar value function or a vector field. And then there's Stokes' theorem. So the integral, the surface integral of a curl is equal to line integral over its boundary curve. So chances are this is a simpler one to evaluate. Or you could be asked to do this and you redescribe this as a surface integral. So Stokes' theorem could be applied either way. Because what could happen here, you have a vector field, you compute the curl, well the curl, for all you know, could turn out to be 0, or at least something a little much simpler than what you had here. So be prepared to try it either way. And finally, the divergence theorem. Integral over solid of a divergence is equal to the integral of the surface integral of f over the surface itself. So, for instance, you may be asked to evaluate this, but you do it by converting it to this and then doing this instead. For instance, as what happened on the third exam, the divergence might turn out to be 0. And then there will be one bonus problem. Now all these problems, so there'll be 5 points each, so all weighted equally. There's a 10-point bonus on differential forms, so from the last couple of lectures. So if you're given a couple of forms, like omega and eta, like from the examples in those notes, you'd be asked to compute something like their wedge product using the various rules involved, or the derivative of a form, or you may be asked to do both operations. All right. So that's everything I'm throwing at you. So useful resources to get an idea more specifically what kind of problems you can expect. Certainly the problems from the take-home exams serve as a good indication, except for certain crazy ones, like that were on the first one. And certainly, all these problems, although there are a lot of them, each one of them will be reasonably tame as far as the actual amount of work that it takes, no monstrous integrals or things like that. So keep in mind, if you set one of these up and you get something that looks really nasty to integrate, that might require something nuts like integration of parts or whatever, then you might want to take a look again. All right. Okay, so first of all, as far as the oral is concerned, that is something, just questions about these operations in general that could show up. Okay. All right.
What does that say at the bottom right there for the bonus?
Oh, differential forms. Yeah. So, yeah. For instance, if I give you a couple of forms,
Oh, okay.
this is what you might be asked to compute.
Okay.
Yeah. Okay. Alrighty. So what I can do during, however much time we feel like spending here, is I can pick out problems of these types and go through them. So if there's any that you would prefer to look at, like maybe you ran into the same kind of problem in one of the previous exams and didn't know how to do it, something like that, then that's something I'm game for. Well, generally, each topic, I did sort of like a one problem per section kind of thing. Like here, there'll actually be like 4 problems on either double or triple integrals, but there'd be like 1 problem on spherical, 1 problem on cylindrical, so it's very evenly spread. Which could be a bad thing, but... Yeah, let's see. I did something like that last semester, didn't I? Yeah, right. Oh yeah, that's right, there was a big long thing. Okay, let's see.
Especially like chapter 13.
Yeah, yeah. Okay, here's what I'm going to do. I will definitely include the statements of these theorems. I will give the definitions of div and curl. Let's see. I will put these formulas on there. Because then once you given that, it's still up to you to pick the right one and so forth. So yeah, but definitely a lot of stuff from chapter 13 that needs to be on there. Okay, another thing I will put on there. For these changes of variable, these for those particular ones, the formulas for, like, for instance, formulas for x, y, and z in terms of rho, theta, and phi from spherical coordinates. So you'll have that. Okay. However, it is up to you to know how to properly translate an integral in terms of x, y, and z in terms of